Hi everybody, welcome back to the Feynman Technique. I know I haven't posted any videos lately. That's just because I have kind of run out of new ideas for Feynman integration. Um, a lot of my new ones have just been kind of old ones with the parameters tweaked, and I don't really like doing that. So I started playing around with other techniques. Now, I'm not a fan of contour integration, but I am a fan of complex numbers and using complex numbers to solve real valued integrals. Uh, so this video is kind of lay the foundation for the technique that I'm going to be using in my next 5 or 6 videos. Um, and it goes like this. All right. So our goal today is to evaluate these standard integrals. You probably all already know what these evaluate to, but again, this video is just going to kind of lay out the basic technique that I'm going to be using to solve some of these other integrals that are not standard. All right. So the first thing we're going to do is we're just going to create this integral with the parameter a. That is the integral from 0 to infinity of 1 over x squared plus a squared dx. And then we're going to factor out a 1 over a squared, giving us the integral from 0 to infinity of 1 over x squared over a squared plus 1. And next, we'll perform the substitution that u is equal to x over a, giving us dx is equal to a du. Applying that substitution, we get the integral from 0 to infinity of 1 over x squared plus a squared is equal to the integral from 1 over a to times the integral from 0 to infinity of 1 over u squared plus 1 du. And we all know that this integral right here is just pi over 2. So this integral right here in terms of a is just pi over 2a. All right. So next, we just recognize, or not recognize, I'm sorry, we let a equal the square root of I. So we're just going to plug in a equals square root of I into this result right here. And of course, square root of I is equal to e to the I pi over 4. Its principal value is e to the I pi over 4. So we plug that in to that integral up there, and we get that the integral from 0 to infinity of x squared plus I, if we plug in I in for our a right here, we get I, or square root of I squared, sorry. If we plug in square root of I into a, we get square root of I squared, which is just I. And that is going to be equal to this, where a is the square root of I. So we just plug in square root of I again. And then we use the 1 over square root of I. We express that in complex exponential form. And then you'll notice that right here, all I did was I multiplied the numerator and denominator of the integrand by x squared minus I. That's a pretty standard technique. And x squared plus I times x squared minus I is, of course, x to the fourth minus I squared. But since I squared is already minus 1, this just becomes x to the fourth plus 1. So now you can see we have our denominator here. And also in the numerator, we have this x squared. And then we have this minus I. But I is very close to the absolute value of I is just 1. So we're getting close to having our original integrals represented there. Okay. So all in all, now we have this. We have that the integral from 0 to infinity of x squared minus I over x to the fourth plus 1 is equal to pi over 2 times e to the negative I pi over 4. All right. And now we'll just recognize that if we can match up the real and imaginary components, so we know that the real part of that integral is equal to the real part of this. Therefore, the integral from 0 to infinity of x squared over x to the fourth plus 1 dx is equal to the real part of pi over 2 times e to the negative I pi over 4. And this was one of the integrals that we were trying to evaluate. Also, we can match up the imaginary components. So the imaginary part of this is equal to the imaginary part of this. Well, the imaginary part of this is just, oh, I made a mistake there. There should be a negative sign here. Okay, yeah, that my mistake. There should be a negative here because the imaginary part is going to be negative integral 0 to infinity of 1 over x to the fourth plus 1. So I'm sure someone will leave a comment pointing out that mistake. So I just figured I'd go ahead and say that I already saw it. All right. But, so pi over 2 times e to the negative I pi over 4, we can use Euler's formula on that. That's going to be pi over 2 times cosine of negative pi over 4 plus I sine of negative pi over 4. Of course, cosine negative pi over 4 is just cosine pi over 4, which is square root of 2 over 2. And sine of negative pi over 4 is negative sine pi over 4. Sine pi over 4 is square root of 2 over 4. So we get this. Pi over 2 times e to the negative I pi over 4 is just pi square root of 2 over 4 minus I times pi square root of 2 over 4. So we're pretty much done. So that's it. We just match up the real and imaginary parts. We know that the integral from 0 to infinity of 1 over x to the fourth plus 1 dx is negative, is the negative imaginary part of e to the negative I pi over 4. Hold on, let me think here. No, you know what? I did not make a mistake here. I did not. All I did was bring the negative over here. That's all I did. I just brought the negative sign from this integral over here. So this was actually correct. Okay, I don't think I'm going to repost this video. It's not that interesting anyway. It just lays the foundation for what I'm going to be doing in the future. But anyway, you can see that matching up the real and imaginary parts will give the results to these two integrals. Anyway, guys, I hope you enjoyed that, and we'll see you next time.